Was talking about the complex number, and then we talked about the circularity of complex number, that I to the power 4 and any multiples of I to the power 4 will be equal to 1, and then how this number I circulates around the real axis is what we discussed later, that once you keep multiplying I, then you will keep circulating on the imaginary and the real axis. Then we talked about real part, imaginary part of complex number, and talked about how complex number is a superset encompassing real number. So now, earlier real number was encompassing all those numbers. Now complex number is going to be one level above the real number, is what we discussed. And then real and imaginary part, and then we started discussing about various properties, summation of complex number, subtraction, whatever be the rules of uh, the game, as in like if you're doing addition or subtraction of complex number, what rules they follow. Then we did talk about multiplication also. Talk about multiplication, and similarly some laws there, and then distributive law was one of the laws which we discussed in the end. And finally, we tried solving some of the problems from the book. We are going to talk about today is basically Argand plane or complex plane. We are also going to talk about basically how the polar representation of the complex number happen. All right. So let's start with complex plane or Argand plane, and actually it will make something clear for you guys, because in your book that's what they have been using. So basically any complex number can be represented on a sort of Cartesian plane. We will not call it Cartesian plane because it's going to represent a complex number on this plane, right? So say for example there is a complex, first of all let's talk about the way this plane would work. So the plane has got two axes basically. One is, again, call it x, call it y, but this will be your real axis, and this will be your imaginary axis. So it will be representing, imaginary axis will be representing any multiples of I. So for example, if I say 1 here, all it means is that it is 1i. If I say 2 here, it means 2i. 3 years means 3i, and so on and so forth, 4 and all that. And if I go on this direction, if I write -1, it will represent -i. If I write -2, it will represent -2i. -3 will represent -3n, and so on and so forth. Wherein on this axis, real axis, when I write 1, it will represent only 1, 2, 3, 4, and so on and so forth, 5. So -1, -2, -3, -4, like this. So for example, you have a complex number like this, that is equals to 2 plus 3i. So it has got its real part as 2 and imaginary part as 3. So when we have to represent it, so the real part is on this real axis, so 2 is here. Imaginary part 3i basically is over here. So this 2 comma 3i will be point over here, and this point will be represented as 2 comma 3, and it will also be called the complex number 2 plus 3i. So basically here it is representing this 2 and this 3. And similarly, if I have to take the distance of this from origin, uh, if I have to take the distance of this from origin, this part is going to be called the modulus of this complex number. This part, whatever I was drawing from here, and this part, we can write it as, this part is going to be 2. We can see it's 2. This is going to be 3. So again, using the Pythagoras theorem, I can just say this is going to represent modulus of z, and this is going to be a, this is going to be O and b. then I can say OA square plus AB square is going to be OB square, and OA square is going to be 2 square, and AB square is going to be 3 square. So OB square is going to be this, and OB is then going to be square root of 2 square plus 3 square, and this is going to be 4 plus 9, which is going to be square root of 13. So this will also be called modulus of z. I did not talk about modulus of z earlier, so let's first talk about that part. So what we did miss out talking about in the last class are two things. One was called modulus of complex number, and then conjugate of complex number. So first, I think you guys know, but I'll just still do this quickly. Conjugate of a complex number. So given the complex number z is equals to a plus ib, we define this as modulus of z. This is called modulus of z, modulus of complex number z, and the value of this complex number is a square plus b square. That's how it is defined. And then I'm writing bar z bar. This is called conjugate of complex number, conjugate of complex number z, and it is represented as a minus ib. So whatever be the sign of here z, you have to actually change it to other one. So if it had been, for example, if z1 had been a minus ib, z1 bar would have been a plus ib. Okay. So now there are properties on both of them, mod z and z bar. So first of this property is mod z square is going to be equal to z bar. So you can check here. One is a plus ib and another is a minus ib. So this is a plus b, a minus b. So this is going to be a square minus b square, and this is going to be a square minus I square b square. So this is going to be a square plus b square. And as we define mod z as square root of a square plus b square, that's the reason mod z square is going to be a square plus b square. So modulus of z is going to be positive always, whether your complex number is positive or negative. And then there are some properties of modulus and conjugate. So whatever be the common property, I'll write side by side, and then I'll write the property which is specific to conjugate separately. So the first property is this, that if you multiply two complex number and take a mod, it will be equal to modulus of first complex number multiplied by modulus of second complex number. This is the property of modulus. So I'm writing it side by side so that you guys can remember it easily. Similarly, the same property holds true for conjugate as well. So z1, z2, whole thing, first you multiply and take conjugate of it. It will be equal to z1's conjugate multiplied by z2's conjugate. Second property is, if you have two complex number and you divide one by other and take a modulus of it, it will be equal to taking a modulus of first one and dividing by it second one and taking a modulus of that as well. Similar property holds true for this as well. So it is going to be z1 upon z2 whole thing. If you take the conjugate of it, it will be equal to z1's conjugate divided by z2's conjugate. So multiplication and division follow this, but then addition and subtraction only happens in conjugate part. So z1 plus 1 minus z2 and whole things taking the conjugate of it, it will be equal to z1's conjugate plus minus z2's conjugate. This property does not apply here. Okay, so all what I mean here is z1 plus z2's bar is not, or plus minus is not going to be equal to z1's bar plus minus z2's bar. Okay, so this is not going to happen. Okay, so these are the properties. If you have any questions here, you guys can ask me. Only thing is, if you have to prove it, maybe we can prove one of these so that you guys understand how these properties are generally proved. So let's take the first case. So I'm taking Z1 as A1 plus IB1 and Z2 as A2 plus IB2. So I'm going to prove the first property. So I'm going to multiply Z1 with Z2. So when I multiply Z1 with Z2, I will get A1 plus IB1 multiplied by A2 plus IB2. And when you multiply, you will get A1 A2 minus B1 B2. I'm writing it in one shot. You guys can check it later. Plus I times A1 B2 plus A2 B1. So this is Z1 Z2. And now if I have to take the modulus of Z1 Z2, then it will be equal to basically square root of A1 A2 minus B1 B2 whole square plus A1 B2 plus A2 B1 whole square. If you go further, what you will get is you will get A1 square A2 square plus B1 square B2 square minus 2 times A1 A2 B1 B2 plus A1 square B2 square plus A2 square B1 square, and it will be plus 2 times A1 A2 B1 B2 basically. This will cancel out, and then from here just take A1 square common. Then what you get is A1 square common, then you get A2 square plus B2 square. You take B1 square common from here, you get again basically B2 square plus A2 square. And then you take A2 square B2 square common, you will get A1 square plus B1 square. Now you can as well write it as the square root of A2 square plus B2 square into A1 square plus B1 square, which is nothing but mod Z1 mod Z2. So this is the first property from the modular side. Same thing you can do for conjugate as well. So we said Z1 Z2 bar, right? So what will be Z1 Z2 bar? So it will be A1 A2 minus B1 B2, and then wherever the plus is, it will become minus of I A1 B2 plus A2 B1. So this is Z1 Z2 bar. Now let's calculate Z1 bar. So Z1 bar is going to be A1 minus IB1 and Z2 bar is going to be A2 minus IB2. Now you have to multiply. Oops. Now you have to multiply Z1 bar into Z2 bar. You will get A1 minus IB1 into A2 minus IB2. So when you multiply, what you get is A1 A2, and then I'm just going to do minus I A1 B2 minus I B1 A2 plus I square B1 B2. So again it is going to be A1 A2 minus B1 B2, because this I square will become minus 1, and when you take minus common it will become A1 B2 plus A2 B1, which is going to be equal to this, right? This is going to be equal to this. So this means that Z1 Z2 bar is going to be equal to Z1 bar into Z2 bar. So the first property I've just proved for both the sides, and this and this. You guys can prove the other properties as well. All right. So, but just remember all these properties, because you might be able to use it to, uh, in various questions, and it will be very helpful. Okay. Now coming to, once we have defined modulus of z, right? Now this modulus of z, and now I'm coming back to complex plane and Argand plane. So this is how we define mod z, and this part OB is called mod z, and any point on this plane can be actually defined like this. So for example, if I have to represent point z is equals to, say again, 2 minus 3, right? What will happen is I have to take 2 on this side, real side, and minus 3 on this side. So the point is going to be here, and then we can represent it using this line. And basically, if I have to write this is as z1, call it z2, call it z1, call it z1, call this z2, mod of z2. And basically my b and b dash, if you guys can look at b and b dash, or z1 and z2, basically z1 and z2 are conjugate, right? So conjugate complex number are mirror image of each other, is, I mean, kind of an observation you guys can make. And this point is going to represent 2 comma minus 3. So again, but the modulus of this is also going to be same. So modulus of z2 is going to be 2 square plus minus 3 square, which is going to be uh, basically equal to square root of that, right? This is going to be equal to 4 plus 9 is going to be square root of 30. As you guys can see, modulus of z1 is going to be equal to modulus of z2. So for two conjugate numbers, also you guys should know that their modulus are going to be same. Alright. Similarly, any other point which has got uh, both the parts of complex number as negative, that is going to be in third quadrant basically. And if it has got a real part as negative and imaginary part as positive, then it is going to be in third quadrant. So let's write that. So that 3, so it would be something like minus 2 plus 3i. So let's say minus 2 plus 3i is a point going to be over here, and this will represent my minus 2 comma 3 point, and I can represent it again using this line. Oops. This is going to represent my mod z3 basically. And fourth point, let's say I'm going to write minus 2 minus 3i. So this is going to be in third quadrant, and minus 2 minus 3 is going to be over here. And then I can just join it using one of the other lines. And okay. So this is going to represent my minus 2 minus 3. All right. So this is going to represent mod of Z4. Move on. Now we will learn polar representation of a complex number. So the same thing, we'll just learn it in little sort of a different way. So now let's say again, same way you have got 1, 2, 3. Here you have got 1, 2, and 3. Okay, just another point which I want to make over here is, you guys understand this. This is basically using the ordered pair, right? So you can see that 2 comma 3 is not equal to 2 comma minus 3, or it's not equal to minus 2 comma 3, or it is not equal to 3 comma 2 also. So 2 comma 3 is not going to be equal to 3 comma 2, because in ordered pair, first part has to be equal to first part and second part has to be equal to the second part. So that's the reason for complex number also, real part has to be equal to real part, imaginary part has to be equal to imaginary part. This is what in the very first class I was trying to mention. Hmm? Now, coming to this side, so polar representation of a complex number is, say you've got a complex number, say 2 plus 3i again. So this 2 plus 3i is a point over here, and I can also represent it using r comma theta. This is what is a polar representation. So what is theta over here is, theta over here is, if you are joining this, then the angle which it is making from the positive x-axis is called theta, and this is called r. So basically R is nothing but mod of Z. Theta is the angle. Theta is also called argument of complex number Z. And theta is basically what? If you are just going to drop a perpendicular from here, so you're dropping a perpendicular from here like this, then cos theta is going to be equal to what? You've got this part, right? And let's call it, just to make sure that it is a generic one, so it's a plus ib. So cos, this is going to be a, this is going to be b also. If so, my cos theta is going to be equal to a upon r, or a is going to be equal to r cos theta. Similarly, my sin theta is going to be equal to b by r, or b is going to be equal to r sin theta. So similarly, z can be represented as a plus ib, right? So r cos theta plus I times r sin theta. So this is how it is going to be represented in a polar form. Only thing which you have to remember here is that theta is going to be between minus pi to pi. This is called principal argument. The principal argument is going to be between minus pi to pi. And basically, how do we define the same way we define theta? So basically, how do we define theta is, say if you have the Argand plane like this, then you have one of the complex numbers like this. So if it is moving in the anti-clockwise, then the theta is going to be positive. This is positive angle. And if we are moving in the negative direction or anti-clockwise, so basically anti-clockwise is positive. Let me write again. Same thing which is we have learned in our trigonometry. Anti-clockwise positive angle, clockwise negative angle. So if this is, so this is going to be minus theta. So clockwise negative angle. So what will happen in this case is that we have to measure angle from here to here, and if your angle is going to lie in this quadrant, for example, if it is going to lie in this quadrant, then you have to measure the angle from this direction, in the negative direction, because your principal argument is between minus pi to pi. So just be aware that whenever they are asking you to change some complex number into a polar form, we have to make sure that we are evaluating both the things, cos theta and sin theta, and understanding where the theta is going to lie. So if cos theta is positive, sin theta is negative, then it's going to lie in fourth quadrant. If both are positive, it's going to lie in first quadrant. If sin theta is positive, cos theta is negative, then it's going to lie in second quadrant. And if both are negative, then it's going to lie in third quadrant. So we remember the same rule applies here as well. So what is the rule here is all sin tan cos, yeah, or add sugar to coffee, all sin tan cos. So everything is positive here, only sin and cosec is positive here, only tan is positive, tan and cot basically, and here only cos and sec is positive. So we remember like this, or some people remember it like add sugar to coffee. So the same rule will apply over here as well. We are actually done with the theory at least. Now there will be questions around it, and we will just do one of the questions so that we understand it well. So for example, in this one, in this question, because it's in the other way, I'll take it. They are saying that convert the complex number minus 16 upon 1 plus root I root 3 into polar form. So what they are asking us is the complex number is given as minus 16 divided by 1 plus I root 3. We have to convert it into polar form. So in r cos theta plus ir sin theta form. So first of all, this complex number is not in the format a plus ib, so we have to convert it. So we'll have to take minus 16 divided by 1 plus I root 3, multiply it with the conjugate of this number, I root 3, just to rationalize this. So what we will get in the numerator is minus 16, and then we will get uh, 1 minus I root 3, and in the denominator we'll get 1 minus I square and root 3 square. Then it will be minus 16. It will be 1 minus I root 3 divided by 1 plus 3. So this will be minus 16 by 4, 1 minus I root 3, and that will be minus 4 plus I 4 root 3. So now we have got our complex number in a plus ib format. So we'll get r. R will be basically what? It will be square root of 4 square plus 4 root 3 square, because r is the modulus of that, right? So because of that reason, 16 plus 48, this is going to be 64, and that is going to be 8. R is always positive, as we said, the modulus is always positive, so we took r as positive. Now my a, this is my a basically. So my a was what? R cos theta is going to be equal to minus 4, and r sin theta is going to be equal to 4 root 3. My r is r 8 cos theta, and this is minus 4. Similarly, it's going to be 8 sin theta, and this is going to be 4 root 3. So in this case, cos theta is going to be minus 1 by 2, and sin theta is going to be equal to root 3 by 2. So now sin theta is positive and cos theta is negative. So what it means, when in which quadrant this theta will lie? Sin theta is positive, cos theta is negative. So in which quadrant this will lie? So where will be my theta? So let's look at the formula which we had. What formula which we had was all sine tan cos, or add sugar to coffee, right? So this is basically my first quadrant. I didn't tell you quadrant probably. This is my second quadrant. This is my third quadrant. This is my fourth quadrant, right? So in first quadrant everything is positive. In second quadrant only sine and cosec is positive. In third quadrant tan and cot are positive. In fourth quadrant cos is positive. So I had sine theta as root 3 by 2, cos theta as minus 1 by 2. So in which quadrant my theta will lie? So now it's going to be in second quadrant, we know. Or if you guys are confused about in this, right? How do you figure out in which quadrant it's going to lie? At least in complex number is by looking at this complex number itself. This part is A, this part is B, right? A is negative and B is positive. So where is A negative and B positive? A real part is negative, and the imaginary part is positive. In which quadrant? This is something which you guys have to remember. Otherwise, you'll not be able to solve the question. As in, when my sine theta is going to be positive. So this is going to be all sine tan cos, and as I mentioned, you have to, if you don't remember, use this acronym, which is add sugar to coffee. Add sugar to coffee. So what is here? A is for all, S is for sine, T is for tan, C is for cos. So all sine, tan, cos. So now once we have got that it is going to be in second quadrant, what we got to do is we have to basically evaluate the angle. So what it means is this theory, as I did right here. So I could have done it here also. Don't have to do it in two places. So basically my point is over here somewhere like this. So my theta, the theta angle is basically this one. So if I have to measure it from this side, it's going to be what? So how do I do it is generally this theta, for what angle of theta the value of root theta sin theta is root 3 by 2. If sin theta is equals to root 3 by 2, then theta is what? Theta is going to be 60 degree, right? Pi by theta, cos theta, tan theta, cot theta, and then sec theta, cosec theta. Then here we have 0 degree. Then we have 30. We have 45. We have 60. We have 90. Then we do sin theta is 0. This is 1 by 2. This is 1 by root 2. This is root 3 by 2. This is 1. Then this is going to be 1. This is going to be root 3 by 2. 1 by root 2. 1 by 2. 0. Then 0. Then this is going to be 1 by root 3. This is going to be 1. This is going to be root 3. This is going to be undefined because this is going to be 1 upon 0. Now, similarly, this is going to be undefined. This is going to be root 3. This is going to be 1. This is going to be 1 by root 3. This is going to be 0. Now, sec theta is just reciprocal of cos. This is going to be 1. This is going to be 2 by root 3. Square root of 2. 2. And this is going to be undefined. And then this is going to be undefined. This is going to be 2. This is going to be root 3 by 2. This is going to be this is going to be what? Sorry, this is going to be 2 by root 3. No, this is going to be root 2. This is going to be 2 by root 3. This is going to be 1. Okay. All right. So, anyways, coming back to this, we are theta is going to be pi by 3, but this is going to be theta is equals to pi by 3. So, my this angle is going to be pi minus theta. So pi minus theta is going to be basically theta is going to be pi minus pi by 3. Okay. So I'm just going to write pi minus pi by 3. So theta is going to be 3 pi minus pi by 3 is 2 pi by 3. So same way, by this theta is going to be 2 pi by 3. Now, if I have to write this in this format, complex number format, then I'll write 8 cos 2 pi by 3 times I 8 sine 2 pi by 3. This is what is the polar form. This is basically r cos theta plus I times r sin theta. So this part is the arguments. If someone asks you what is r, what is theta, so r is 8, theta is 2 pi by 3. Z is equals to a plus ib, and if I say that give me the multiplicative inverse of it, z inverse, what will be that? Or rather, what is the property of, if I say z into z inverse, what it will be equal to? Multiplicative inverse says that if you multiply this complex number with its inverse, you will get 1. Okay. Yeah, so this is the property. Let's go back and look at our question. So I have to write it like 3 plus 4i first of all. And I have to calculate inverse of it. So it's going to be 1 upon z. Okay. Why? Because if I multiply it with this, it will be 1. And now this is going to be 3 plus 4i. Now this is 3 plus 4i. So what I have to do? I have to multiply it with the conjugate of it to rationalize it. So 3 minus 4i. Once I do 3 minus 4i, then this will become 9 and this will become minus 16 I square. Then this will become 3 minus 4I divided by 25. I'm just doing it in one step. So this will be 3 upon 25 minus 4 upon 25I. And if you multiply 3 upon 25 by minus 4 upon, so let's do that. 325 minus 4 upon 25 I. If I multiply it with 3 plus 4I, so let's see what we get. What do we get? We get 3 by 25 into 3 plus 3 by 25 into 4I minus 4 into 3 by 25I minus 4 square I square 20 upon 25. So this will cancel out because 4 into 3, 3 into 4, right? This will become 9 upon 25, and this will become what? Plus 16 upon 25. So this will become 25 upon 25 will be 1, right? So that's why this part 3 upon 25 minus 4 upon 25I would be your multiplicative inverse. This one is also easy. You have to just rationalize it. Whenever you get something as a denominator, as a complex number, just try to rationalize it. This is the very first thing you try to do. Then probably your things will be easier. In this case also, if you had done that, probably it would have become easier. All right. This one we had done in the last class. It's okay. Now this is what? Write the conjugate of 3 plus 4, right? So it's simply, just now we have learned to write a conjugate, whatever be the sign here, plus will change into minus. So it's very easy. But what about this? Write the conjugate of 5i divided by 7 plus I. We have to write the conjugate of 5i divided by 7 plus I. Conjugate of. So as I said, if any complex number is in this format, 7 plus I, first rationalize it. So I'll multiply it 7 minus I, 7 minus I. What will happen in the numerator is it will become 35I minus 5I square divided by this. So it will become 49, and this will become minus I square. This will become 5. 5 minus 5 square will become 5 plus 35I, and this will become 50. Now will become 1 upon 10 plus 7 upon 10I, and then we have to write the conjugate. It is simple from there, but I just have to change the sign. 1 minus 7 upon 10I. So GP like this, AR square, and it's like AR to the power n minus 1. So up to n terms. Then the sum up to n terms is A into R to the power n minus 1 divided by R minus 1. When R is basically greater than 1. Or you can just write A into 1 minus R to the power n divided by 1 minus R when R is less than 1. So in this case, you had I square plus I to the power 4 plus I to the power 6, and it was going up to 2n plus 1 terms. So if you have to use the formula, here A is I square, R is I to the power 4 upon I square is again I square. So if you have to use the formula Sn, so in this case it's Sn S2n plus 1. So the first term is I square, R is I square to the power basically in place of n you have to write 2n plus 1, and then you can write minus 1, and then in the denominator again you can write I square because R is I square minus 1. Now your I square is going to be, oh, you can just simplify, start simplifying probably. You can write I square as minus 1. Similarly, this is going to be minus 1 to the power 2n plus 1 minus 1, and divided by this I square is going to be minus 1 and minus 1. So your numerator is going to be minus 1, and any power of minus 1 and that is odd, then it's going to give you minus 1. Minus 1 minus 1 divided by minus 2. This will cancel out. So you will be left with minus 1. You guys could have observed it in a different way also. So if you look at I square plus I to the power 4 plus I to the power 6 plus I to the power 8, this is the way it is going, and this is going up to 2n plus 1 terms. So if you are going to solve it in other way, so I square was minus 1, I to the power 4 was 1. So club it together. Then similarly, I to the power 6 is again going to be I square or minus 1. I to the power 8 is going to be 1. So in this way, basically up to 2n terms, the same thing would have continued. So what I mean is, this entire thing is 2, this entire thing is 2, 2 to 4. So up to 2n terms, this is the pattern which would repeat. And the end, again, the first term would remain as minus 1. So all this will become 0. So up to 2n terms, the things will become 0, and what we will be left with only minus 1. So you can just see in this way as well, you will get the answer as minus 1. Yeah, so basically it's like clubbing two numbers together, and every two numbers basically when I'm summing up, it is coming as 0. So this is 2 into 1, this is 2 into 2 basically, I mean 4 terms, right? Up to here 4 terms. So up to 2 into n terms, this is what is going to repeat. Everything will become 0. And the last term is basically starting with I square only. So I square will remain, and that is why it will be minus 1. So either you can use the formula for GP and solve it, or you can just observe it and solve it as well. So I'll just take up this question and show you how to find out the square root of a complex number. So they've just given you a formula, but rather, I mean, no. And then formulas are fine if you can remember. If you don't, then probably the best approach is to know how to solve it. So they are saying that you have to find the square root of this number. The square root of 7 plus 24i. We have to find the square root of this. Uh, so let's say, because we know that if you take even square root of a complex number, it will be a complex number. So we assume that the square root of this complex number is x plus iy. Now one side is x plus iy, another side is in square root. So what we will do is we will take the square on both sides. What I'll get is x plus iy whole square, and this will be 7 plus 24i, because I've just taken the square on both sides. This will become x square plus I square y square plus 2xy I, and this will become 7 plus 24i. Now this part will become x square minus y square, and this will become I 2y xy, you can say that, and this will become 7 plus 24i. Now as we know that if two complex numbers are equal, then their real part and imaginary parts are equal. So we know that x square minus y square is going to be 7, and then 2xy is going to be 2xy is going to be equal to 24. Now I have got some equation x square minus y square and 2xy. So what we will do is we will find out x square plus y square. Why we are doing it is because if we get x square plus y square value, then I can just take two equation. One is x square and y square, and another one is x square plus y square, and then I'll just be able to basically solve these equations. So what I'm doing here is I'm writing x square plus y square whole square. So if you guys know, a plus b whole square is going to be equal to what? A minus b whole square plus 4ab. I can write it, right? Because what? X is a square plus b square minus 2ab plus 4ab is going to be equal to a square plus b square plus 2ab. So now I'm going to write x square plus y square whole square is equal to x square minus y square whole square plus 4 times x square y square. So x square minus y square is 7. So 7 square is 49. 2xy is 24. So whole square of that will be 576, and this will be equal to 625. So my x square plus y square will become square root of 625, which will be 25. So I'll not take plus minus because both of them are positive quantities, so it should not be negative. So x square plus y square is equals to 25. And now I have x square or minus y square is equals to 7. When I add both of these together, oops, then what do I get? I get 2x square is equals to 32, 25 plus 7. X square is equals to 16. Now x is equals to plus minus 4. When x is equals to plus minus 4, then y square is going to be, I just put the value here, there will be 16 minus 7 will be 9. So y square is also going to be plus minus 3. Now, what was my complex number? My complex number was x plus iy. So I've got x is plus minus 4 plus iy is got plus minus 3. So plus minus I times 3 is going to be the square root of the complex number.